This is our third conversation on Chapter 10. You might find this one a little challenging. You might need to watch this one a couple times to make sure that you understand the ideas that we're talking about here. We reviewed projectile motions and very quickly looked at fast-moving projectiles, remembering that it always takes the same amount of time for my projectile to land, but the range is dictated by how fast I launch it. We're going to chew into circular satellite orbits here, and then the rest of the chapter is ideas more than calculations. So let's go back to our girl throwing her projectile, and the speed of the launch has to be fast enough to match the curvature of the Earth. The speed is constant, but the velocity is not because the direction is changing. Real quick, when satellites are launched, this is a case where air resistance is incredibly important. So the launching of a satellite and the return of something from space is hugely impacted by air resistance. And to have a satellite work effectively, it needs to be outside of the Earth's atmosphere, about 150 kilometers or more. And something like the International Space Station periodically needs to boost itself outward to make sure that it stays clear of the Earth's atmosphere. Remember that motion is moving in a direction, circular motion is moving in a direction perpendicular to the centripetal force, which is the force of gravity. The period is the time that it takes for a satellite to go around the Earth. Could be 90 minutes for the things that are closer, could be longer for higher altitudes. So that depends on its radius, its distance from the center. And we'll be reviewing what we learned about circular motion as we talk about satellites. Here is a picture that looks like the last one of the girl throwing the ball. And remember that in a second, our projectile drops about 5 meters. Well, by coincidence or by measurement, the curvature of the Earth is such that if you travel 8,000 meters, 8 kilometers, the curvature of the Earth drops about that 5 meters. This is an important thing to remember, that we're looking at straight lines compared to the curvature of the Earth. Remember our bowling ball. Again, back to our very first day of class. When we pushed our bowling ball, it moved. It continued to move. Here's a question for you: when that bowling ball was rolling down the hallway, was gravity acting on it? Well, yes. Gravity existed in the hallway. Did gravity make the ball go faster or slower? We're ignoring friction. And no, gravity had no impact on the speed of the ball. Why was that? Well, because if you imagine if you are drawing vectors, your motion was in the direction of the hallway, and the motion due to gravity is this way. So they were the direction of motion was not the same direction as gravity. So the only thing that gravity did was had the floor give a normal force against it. So there was no opportunity for the ball to move vertically, to go downward. So gravity did not impact the speed or direction of our bowling ball. How does this relate to a satellite? It's the same thing. The gravity, the centripetal force, is acting on the satellite, but it's contrary, it's opposite to, or it's a different direction than the direction of the motion. So the centripetal force, the gravity, is only pulling the satellite inward, just the same way that it's keeping the bowling ball on the ground, but it's not impacting the speed at which it is moving. Think about that. That's a hard one to get your head around. All right? Imagine Imagine then that we had the ability to make a bowling alley that circled the Earth. And imagine that we had a bowling ball at a given speed going around the Earth. And we're far enough out that there is no air resistance. What happens to the motion of that bowling ball that is spinning around the Earth? Now, I've given you a sketch here of our idea of motion, and we have the inward drawing force, and we have our velocity. But we also have inertia. We've got this conservation of momentum. There's no force acting opposite of the velocity to cause it to change. Think about that for a minute. So gravity would not, if our bowling ball were on a ramp above the Earth, is it any different than the bowling ball in the hallway? Does gravity change its direction? Does gravity change its motion, its speed? And the answer to that is no. Well, here's the question for you. What if our bowling alley were not continuous and there were a gap? And we'd have to be playing Evel Knievel and seeing if our bowling ball could go. How fast would our bowling ball have to go to not need the support force of the alley underneath it, but be able to continue in its circular orbit? So what speed does our bowling ball need to be going to clear the gap? That's interesting. That's an interesting question. Well, if it were to fall, if our bowling ball were to fall off the gap, now it looks like our projectile. Now it looks like the car driving off the cliff. And what is happening to the speed? Well, now that there's no support force, now that there's no support for the bowling ball to not be pulled, not to be taking the inward seeking force, it's going to gain speed. So its circular path, in fact, changes into a parabolic path. And it will be going faster and faster as it goes toward the ground. All right? So what speed would it take? And remember that the ground is dropping off at the rate of, it takes 8 kilometers for the curvature of the Earth to drop such that we fall 5 meters in 1 second. So the question is, how fast would I need to be going to clear this? And the answer is that if I'm traveling at 8 kilometers a second, I catch up with the ramp on the other side. All right. If the ramp were not there, would the ball continue in the circular path? No, it would be in a straight path. And falling downward. Think about this. We will work on it in class. Here's something to think about when we toss a projectile sideways. So we introduce no vertical component. It curves when it falls. If the curve if the curve matches this, it will be an Earth satellite if it matches the curved surface, goes in a straight line, or spirals. What's the answer? Well, in fact, so long as we are at the speed so that the parabola at which it drops matches the curved surface of the Earth, the projectile will stay in orbit. Here's another question for you. When a satellite travels at a constant speed, what is the shape of its path? Is it circular? Is it elliptical? Is it an oval? Is it a circle with a square corner? Now, a satellite traveling at a constant speed will be in a circle. So when we're launching our satellites, the engineering behind launching a satellite is to be vertical to escape the Earth's atmosphere, and then when you're out of the atmosphere, to move to be horizontal and to make a thrust of 8 kilometers per second so that it falls toward the Earth and stays in orbit.